All right, good morning, everyone. I'm not going to keep this outfit on the whole time, but just for context, tomorrow's Halloween. My daughter's a unicorn, my son's a dragon, so, wizard. Oh, it's so warm under that thing. Anywho, so it's a fun thing to do. Hopefully, take some stress off you all. So, yeah. Test 2 is coming up a week from today. I've been working diligently, so I made this draft for the test, and instead of polishing the test, I prioritized making the review. So the review is 90% complete. It is missing inductors, which we're going to cover today anyway. But I'll have the review finished by then today, but it is available. The review is available, summaries. Someone asked for this, and so, the review in general, people appreciate, but one of the slides in here that might be useful is there's a right-hand rule slide with all the right-hand rules and all that stuff, so this is what we're going to go through on Tuesday. There's no answers. There's problems in here, but there's no answers. We'll find the answers on Tuesday. It'll be a grand time. So the test is on DC circuits. So, we just kind of quickly zoom through this. DC circuits and then everything to do with magnetic fields. So we have the DC circuits with the right-hand rules. So forces on moving charges due to a magnetic field, sources of magnetic fields, Faraday's law, and then we'll do inductors today, which are just solenoids. So those are there. I also quickly put together this morning all the clicker questions into one PowerPoint slide, so those are there, with the exception of the inductor ones, since we're going to go through those today. Reminder to you all that this PowerPoint, this one's in order. I'll make one that's random once they're all there. Reminder, this one has all the answers in it, but if you open it in a PowerPoint, you can hide the ink. If you're like, what does he mean? Remember in PowerPoint, if you go to review, there's a button here that says hide ink. So this PowerPoint currently doesn't have any ink, but if I scribble some nonsense in it, I can make said ink disappear by just clicking that button. So you can hide all the answers by doing that, if you so desire. So today we're going to finish up inductors. I think I told you all last class, sadly, we're not going to get to AC circuits. Now, I did make the entire PowerPoints for AC circuits. So if you want to learn about AC circuits, I did post those PowerPoints, but we're not going to actually go through them as a class. So we have test 2 next week. So this coming Tuesday is review day. And then the Thursday is the test. After that, the following Tuesday is Veterans Day. There's no class on Veterans Day. What day is that? Yeah, something like the 11th. There it is, the 11th. Are you Harry Potter? No, I was going for Gandalf, but and what's Harry Potter? I'm more of a Lord of the Rings person than Harry Potter person. Anyway, so we're gonna finish. We'll have 3 days after the Veterans Day. We're only gonna have 4 more classes. So Veterans Day is the 11th. Then we have 1, 2, 3, 4 classes. The 4th class is the week of Thanksgiving. That last day, the week of Thanksgiving, that'll be a review day because that is our last class. So that'll be a review of kind of everything. Obviously, I won't cover everything. I'll mainly be emphasizing the stuff from test 1, honestly, because that'll be the stuff that you might have forgotten. But the 3 days we do have are all going to be focused on electromagnetic waves. That'll be the last thing we cover. Now, with that in mind, a couple more logistics things to note about you all the things. One, I have the most updated formula sheet. This is the one that I'm currently planning on putting on the exam. So this formula sheet is posted. It's got a couple things it didn't have before. I've got omega equals 2 pi f. I have EMF equals BLV. If you don't know what those are used for, that's good to look into that. I think that's the only 2 new things I added. I updated the rubric, but I guess it didn't update here for some reason. All right, I'll double check this. I did update the rubric. Remember I told you all the free responses going to be worth 12 points? What I did to the rubric to update it, again, sad that it's not updated on here. I thought it was. Let me jump over to that one and see if Maybe I'll get lucky and this is the one that's updated and I can just swing it over. So it's out of 12 points. Yeah, good. 1 to 3 points will be for the accurate picture and the variable that you're solving for. Actually, I might make this 1 to 2 points and might make this one 3 to 4 points. I might do a tiny little adjustment actually. I'll just do that now. And then I'll upload it. So 1 to 2 points for identifying what you're solving for and drawing a picture. 3 to 4 points for identifying what you're solving for, or the givens that you have. And then the rest of the points, a big chunk for did you identify the right equations and use them appropriately. And then the last 2 points are just did you do everything correctly or did you make a small mistake. So that's kind of the main, that's how the breakdown's going to be. Just kind of expanded some categories. Remember, if you write the right equation, if you've identified the right process, that basically gets you half the points. Now, still do the picture, still do all that kind of stuff to make sure you get those points as well. But yeah, I'll go ahead and just sling this in there. So there's that. Other update for you is because we only have inductors this week, and inductors is actually such a small section, we're just going to finish it today. There's no point in me giving you all an entire quiz on something I covered in one day. So there's actually not going to be a quiz that opens this week. So let me make sure this is very clear, because I don't want to get a bunch of emails about this. I know how this stuff goes. There is a quiz on Faraday's Law. That is due this Saturday. That quiz exists. Faraday's Law, due this Saturday. Make sure you all do that. Don't miss that. It's here. What I removed is I removed the quiz on inductance. That one was going to be due next Saturday. There will not be a quiz on inductance because honestly it's quite simple. In the problem set, the section at the bottom with inductance and AC circuits, the inductance is only 3 questions you can actually do. So in the problem set, it's just the first 3 questions that are inductance, and then the rest is AC circuits. I'll also clean that up today and send that out. Yeah. When does recitation end? When does this say it end? That's November 17th, that week. So the week before Thanksgiving. So we're only going to actually have one more quiz. So again, we have Faraday's. There's a quiz this week that's due for Faraday's. After test 2, there will just be one more quiz on light. Because we have 3 class days, so we'll just make one quiz for all 3 of those days. So it makes 10 quizzes total, which is a nice round number. All right, so just update on that as well. It doesn't change anything for you this week, but it does mean that next week you do not have a quiz to work on.
Sorry, so the test is 60 multiple choice?
Yes, the test is currently planned to be 16 multiple choice. 3 for response. Pick 3 out of 4. There'll be 4 for response provided. We'll pick 3 of them.
And they're 1 part.
Yes, and they're 1 part. So the test should be a little bit shorter than the last test. Not a ton shorter, but a little bit.
I'm guessing that right-hand rule is applied to
30 to 40% of the if you can't do right hand, yeah, it's a lot. Yeah.
What would you do if someone throws their hand
I'd work. They use their left hand. It's fine. Yeah. All right. So inductors. This is the new thing. Oh, any quick questions about the test or any jazz like that?
Oh wait.
I don't answer it now. Then emails.
Final exam.
Final exam is going to 5 by identify. That will be all multiple choice, roughly 40 questions.
You said it's not. You said this test isn't going to be on AC circuits.
This test will not have AC circuits. It will have DC circuits. Yep. We're not even covering AC circuits in this class, sadly. I made a whole PowerPoint on it. We just don't have time.
Are we covering this?
Oh, yeah. This is what we're doing today. Huh? Sadly, no. I chatted with some people. It's basically they do AC circuits or do electromagnetic waves. I only have enough time to do one or the other well, and so that's why. But I did make a PowerPoint slide on AC circuits if you want to check it out. Things like that. Yes, inductors will be on the test. We're going to cover it today. Yeah. All right. So let's go ahead and run through this. Inductors. Inductors are something we've learned about. An inductor is a solenoid. It's a solenoid that's placed in a circuit. We are going to kind of place them in circuits at the end to understand what they do, but we're not going to actually do any math with them in the circuits for the sake of time. So, you need to know magnetic fields, you need to know about source magnetic fields, magnetic flux radius, all the things you've been covering. And this is basically a practical application of them. So we're going to talk about what inductance is. We're going to derive it for a solenoid. That's the only thing we're going to really care about. And then we're going to talk about how you can store energy in it. The way to think about an inductor, so if y'all remember from test 1, we had capacitors. Capacitors had an electric field in them, a constant electric field. They stored energy. It was great. Inductors are the magnetic field equivalent of a capacitor. So you have a capacitor that stores charge, and it stores an electric field. We're going to have an inductor that stores, quote-unquote, a magnetic field. So this is kind of the analogy there. Yeah.
Sorry, are conductors on the test at all? Anything with that? I'm sorry.
Capacitors? No capacitors in the test. Yeah. All right, so what is inductance? This is just a definition. Right now, this is just a definition. It's not derived from anything, it's just a definition. It says the property of a device that tells it how effective it is at opposing a change in current. So right now, I'm just telling you the definition, then we're going to understand this definition as we kind of apply it. So this definition, it's inductance. The unit for it is a Henry. So if you say, hey, what's the inductance of this device? I might say 3 millihenry, or 3 microhenry, or 1 Henry, though a Henry is quite large. Henry, so there's a nice, if you haven't noticed this, every single unit I've given you for like every single new variable is named after someone. You got forces named after Newton. You got current, the unit's named after Ampere. That's a person's name. You have resistance, ohms, is named after a guy, last name Ohms. Voltage is named after a guy with last name Volta. Magnetic field is named after a guy with last name Tesla. Capacitance is named after a guy with Farad. Farad actually was someone's name. Every single unit I taught you in this class is named after someone because they were all discovered in the last 200 to 300, maybe 400 years. And so in that time frame, people named things after themselves. Before that, distance. Who discovered distance? That's a way more nebulous, like that's way harder to pin down. So meters, I don't know where that came from. It's not named after someone. But the unit is Henry. And then if you put it in terms of other units, mathematically it comes from this volt times second divided by amperage. The symbol for inductance is L. And this is kind of unfortunate, but it is what it is. We cannot use I for inductance. It's already used for current. Yeah, Greek, I don't know. I don't know what the Greek I actually is. They chose L. I don't actually know why they chose L. The thing that's slightly unfortunate here is up to this point we've used L for length. This will be something that happens in your classes where letters are used for more than one thing. It's just how we only have so many letters in the alphabet. It's how it goes. How do you know which one it is? Context. How do you know which one it is? Based on the equation it's in. We have the same, remember, math is a language. You all have the same problem in the English language. The word can mean multiple different things depending on the context of the sentence it's in. I can do something, or go buy a can of green beans. It's the same word, it means two different things. How do you know what it means? Context, the equation. So, math is a language, same thing. You've done it you've done it for most of your life. This is just doing it in a different context. All right. So, this says that the voltage that a device generates is equal to its inductance times the rate of change of current through it. So this inductance basically tells us, as my rate, so say my current's changing 5 amps every second. I multiply that inductance, and that's going to tell me the voltage of that device. What does voltage do? Voltage, in this case, is the negative. It's going to oppose the voltage that's being applied to it. It's going to counteract that. And it is EMF, yeah. This EMF acts like a voltage, and you can measure it across the device. Fun fact, every single conducting object has some impedance. Every object has resistance. Every object has capacitance. Every object has impedance. So for electrical engineers, this is something you have to be careful of. When you get to really small devices, so, where is this inductance coming from? Why is it happening? We've been talking about this in class. If you have a loop of wire, and there is a changing magnetic field in it, we just learned last class, what happens? The loop opposes that change. Whatever is happening inside this, whatever is happening to the flux, it opposes that change. So why am I mentioning this? Your phone is filled with wires. And guess what? One wire makes a field, the other wire experiences the field. So every single wire in your phone is making magnetic fields, and every other wire in your phone is experiencing those fields. And every single circuit in your phone is a loop, otherwise current can flow through it. So your phone is filled with loops that are making fields, experiencing fields, and those currents vary with time, and long story short, they all affect each other, and you have to account for that. When they're really close to each other, you do. This is not a concern on like a large scale, but when you work with stuff that's really close together, this is something you have to worry about, is that every single current-carrying wire makes a magnetic field, every other current-carrying wire experiences that field, and you get this Lenz's law effect, and it's something you just have to deal with.
Probably a stupid question. What was impedance?
Yeah, it's this definition here. The property of a device that tells us basically as the current changes with time, how much voltage does that device generate to oppose that? Yeah, so we're going to see some examples today, and that's going to help us understand this. We start with the definition, and now we're going to start kind of exploring it. So the first one, we're just going to do a very quick math one. Even if we don't understand what impedance is, we can at least hopefully use the equation. So what is the rate at which the current through a 0.3 Henry coil is changing if an EMF of 0.12 is induced across the coil? So there's some change in current. That change in current is causing there to be a voltage. We learned about that last class. And this device happens to have an inductance of 0.3 Henrys. Why does it have that inductance? Because we'll learn that later. We'll learn how to calculate the inductance based on its geometric properties later. But yeah, just basically simple, can use the last equation that I put up there. Now you get to watch me log in because I didn't do it ahead of time. All right. So yeah, go for it. Is the rate at which current changes 0 amps, 0.036 amps per second, 2.5 amps per second, or 0.4 amps per second? It is not. Thank you. Now it is. Boop. Thank you. It is worth writing it out. It's a new equation. If you try to do it in your head, you have a much higher chance of making a mistake than if you write it out. That's a rule of thumb in any of your classes forever. All right, give you all about 20 more seconds. Yeah. What is the what? Inductance. Yep. All right, in 3, 2, 1. All right. So first thing, we're going to identify what we're solving for. We are solving for the rate at which current flows through this device, di dt, the rate of flow. Am I gaining more current or am I losing current? So we're solving for that. Then we look at our equation. We got L and we got EMF. So then we just go to the equation that relates these, which is EMF equals negative L di dt. Now we're just going to kind of ignore this negative, because all this negative does is explain the y, but what does a negative current mean? It just means it's going to oppose the direction. Negative here is the direction of current, but it doesn't really, there's not enough details to determine that. I didn't ask for the direction, nor would you have enough information to figure that out. So, you just rearrange this. di dt equals epsilon over L. So that equals 0.12 over 0.3. If you divide a number by a bigger number, you should get a smaller number than 1. So it's 0.4 amps. Great. Just some math. Very nice. Okay. So let me quickly kind of walk through why it's called self-inductance. Now, up to this point in the class, I've been telling you that something cannot affect itself. And that is still true, but what I have to kind of convey to you all is that what a solenoid isn't just one object. So here's what's happening here. This is the kind of principle here. We have some voltage source. I don't care what it is. Let's just call it 5 volts. And it's going to go through a loop of wire, and then go out the other end. Great. Current's going to flow through that. Now, let's actually make this a switch so that there's originally no current. Great, no current. Single loop, no problem. This will actually have no concerns. But what if there was a loop on top of this loop? In fact, what if this was, instead of just one loop, it was 2 loops? Why am I saying this? 2 loops are effectively, you can think of them like 2 objects. So here's what's going to happen. When I close this switch, well, actually, before I do that, how much current is going through this loop right now? None. What's the magnetic field in this loop right now? 0. Hopefully we're all cool with that. When I close the switch, current's going to start to flow. Now, it's not going to happen instantly. As I close this, current's going to want to start to flow. As current starts to flow through this wire, let's just practice right-hand rule. I know this picture's kind of jank. The current here is going to flow, just to make this really clear, the current's going to flow, counterclockwise. Go ahead and quickly find the direction of the magnetic field made by counterclockwise wire. This is good practice. See if you remember how. Spend 10 seconds on it. All right, so you wrap your fingers around. Which way is the magnetic field going to be generated? Out of the page. Now, here's the idea. One of these loops, the way we can think about this, one of these loops will start to make a magnetic field that changes with time. This is not instant. I don't just go from 0 to something immediately. That's not how the world works. There's always a connection between the two. As one of them gains current with respect to time, it makes a magnetic field that changes with time. Changing current makes a changing field. Why does that matter? I have 2 loops. So one loop makes a field that changes with time. The other loop sees a field that changes with time. It doesn't like that. So one loop is making a field. Let's just kind of draw it over here. So one loop is making a field, if my pen would work, not finger painting. That changes with time, and the other then will experience that field. Great. No, it doesn't like it there. Doesn't like it anywhere. All right, so as it makes it out of the page, the other one's going to counteract that. Which way is that other? So if I'm getting more field out of the page, what's the other one going to do? How do you counteract out of the page? Into the page. It's going to try to make a current that opposes the other loop. Yes, they're connected together, but we can pretend like they're separate. This is what self-inductance is. This is why we call it. If we go back to the previous slide, this is the idea. This is why it opposes a change in current. It's a bunch of loops, and each loop is trying to make a field, and every other loop is trying to oppose that field. So the loop is kind of fighting itself. Now, why is it fighting itself? Because it's like, you can imagine it like a bunch of separate loops that just happen to be connected.
Do the loops have to be circular here?
That's a great question. They do not have to be, but they always are. No one's making, and the reason for that is, one, we have the equation for a circular loop. The other reason is just functionally. It's really easy to wrap a circular wire. This is something you can do at home. If you have a wire and you have a rod, just hook a drill up to it and spin it, and it's going to make a nice circular loop for you, whereas a square loop would be awful. And yeah, sharp corners sometimes have some problems. All right, so yeah, one makes a field that's going, in this case, out. How do we counteract going out? We make some in, and it's fighting itself. Self-inductance, fighting itself. Yeah, because it's fighting. One of them's going to make it out, one of them's going to fight it. So
you said in. You said out with it from in.
Yeah, there's both. So one makes a field. Oh, yeah, you're right. It's backwards. Yeah. Good catch. X's and dots. Yeah, it ends up being the same thing, but just to make my wording match, one makes a field out, and the other counteracts it in. Yeah. to switch the spots on. That's good though. All right, so this is the idea of self-inductance. This is the logic. This is a thing that happens in circuits. And this is very, very useful, so we're going to unpack that more as we go into it. It's very useful to have things that fight a change in current. An easy example of that is when like lightning strikes your house or something near it. I'm going to go from some current, and if that lightning is going through your circuitry, a lot of current. I don't want a lot of current going through my devices. That's going to break it. So if only I had a device that could oppose a large change in current that arises sporadically. Grounding can help, but not always avoid it. So inductors can be a device in your circuit to fight these changes of current that sporadically arise.
Would the second loop, since the field is going into the page, make the current?
Yes, it would make a current the other way, and that's the whole idea here. Yep, these inductors, and that's actually something at the very end of the PowerPoint we'll see, they oppose the change in current, and so they basically make the current take a longer time to flow through the circuit, to reach its max value.
Sorry, so you said we're mainly focusing on solenoids, right?
Yeah, that's the only type we care about.
Reiterate again what a solenoid is.
Yeah, a solenoid's like a slinky. It's this, but a lot more coils. We'll see some pictures of them in a second.
Does it do anything just like literally just doing this? That's not a inductor.
So this is a solenoid.
Like what's the point of this? A lot of loops?
It's a lot of loops. The magnetic field is uniform in it, just like in a capacitor, the electric field is uniform. In a solenoid, the magnetic field is uniform. Yeah, so that's the benefit, and we're going to use it to derive some expressions. All right, this one, the wording here isn't the best, but it's just, so I'm just going to talk through it. That's actually, because the wording here isn't phenomenal, and I haven't figured out how to improve it. How does the inductance for an object change if at some time it has a current of 5 amps through it, and another time it has a current of 10 amps through it? So if you're like, what does he say here? At some point, it's a constant 5 amps. At another point, it's a constant 10 amps. And my question is, how does the inductance affected by this? If we look at our equation, so if we just rearrange this, and I guess this becomes a problem. If it's a constant, what's the bottom?
0.
If it's a constant, what's my rate of change in current? It's 0. So what I'm trying to convey to you all here is inductance doesn't care about how much current's going through it. That's the whole point. This PowerPoint slide is not the most eloquent. It's not one of my best slides. The point of this is to show you it's about the rate of change, not how much current. We don't actually care how much current. We just care how quickly it's changing. Now, what we are going to do is we're going to derive the inductance for an inductor. And I'm going to keep mentioning capacitors. Because if you all remember capacitors, you can go to Ace Hardware and you can buy a capacitor. And if you buy a capacitor at Ace Hardware, it's going to say 5 microfarad or 3 millifarad. That is just capacitance. You can do the same thing with inductors. You can go to a store, you can buy an inductor, and that inductor will have an inductance of 5 millihenry, 10 microhenry. Why am I saying this? It's not connected to anything. Inductance doesn't actually, we don't determine inductance by taking a measurement by putting it in the circuit. When I go to the store, none of those inductors are connected to a circuit. They're all just on the shelf by themselves. So we're going to derive the equation for inductance, and we're going to find it actually, the way we determine inductance is not based on the circuit it's in, it's based on how it's built. It's based on the geometric properties of the material, just like a capacitor. If you all remember, capacitance equal to epsilon naught A over D. How do you determine someone's capacitance? How big is the area of the plates? How far away are the plates? And technically, is there an inductor? Is there a dielectric in it? We're going to do the same thing for a solenoid. That's what I'm trying to prepare you all for. All right. So, here's where we're going to start. L equals epsilon di dt. And every step I'm about to do is something you all are capable of doing. We're going to use equations. We're going to use only equations that we know. So, first step. We're going to look at this equation, and we're going to remember the definition of epsilon. I'll give you all a moment. See if you all remember the definition of epsilon when the flux is changed. It has to do with flux. Look for the equation that has to do with flux. See if y'all can find it. Give you all a few moments. EMF equals, and it has to do with flux. Why do we get an EMF when the current change, when the flux changes?
Respect to C.
It ends up being that way, yes. All right, so the EMF is the number of loops you have times the change in flux with respect to time. That's the definition that we've been using. This is why we get an EMF, Faraday's law. So now we're just going to plug that in. So L equals, it's an absolute value. We're not going to worry about the negative sign. You don't go to a store and buy a negative 3 millihenry. There's no such thing as a negative inductance. D flux dt. And we're going to do something that physicists are cool with, mathematicians aren't. It's fine. The way physicists view these derivatives is we just pretend like these are infinitely small things. Mathematicians view them differently, but it ends up working out fine. So this is an infinitely small amount of change in flux. This is an infinitely small amount of time. This is an infinitely small amount of current. Why am I saying that? We're just treating them like variables. And why is that relevant? If, fractions keep flip change, we're just going to cancel out those dt's. If we treat them as a variable, we can do that. Seems weird, but it's fine. All right, d flux dt. All right, now, what is the equation for flux? See if you all remember the equation for flux. We're going to take that and put that in there. Oh, you're right. That's supposed to be I. Thank you. Yeah, d flux di. So we're going to take the derivative now of flux with respect to I, which again seems silly, but it's fine. You just need to remember, all right, so equation for flux, I'm hoping this one is, you've seen this at this point. I mean, you've seen it. I hope it rings a bell though. BA times cosine theta. So we're going to chuck that in there. So we get that inductance. We're just solving for inductance, so it's just going to keep showing up here. D times B times A times cosine theta over DI. Now, we're looking at a solenoid. So everything in this equation has to do with a solenoid. What is the B? It's a magnetic field made by a solenoid. What's the A? It's the cross-sectional area of a solenoid. What's the theta? It's the angle between the magnetic field made by a solenoid and the area of a solenoid. So if we draw a solenoid up here, and we had the current going this way, I don't know if you looked at it from the right side, it's counterclockwise. The magnetic field made by this solenoid that I drew up here points to the right.
Is that a W?
N. Yeah, it's a little sloppy N, but it's an N. All right, it makes a magnetic field to the right, which way is the area vector? Also to the right. What's the angle between them? 0. Yeah. Right hand rule 2. So that's going to be 0. The area of my solenoid doesn't change. Why? Because it's a uniform solenoid. No one's making solenoids that area is very over. Maybe some people are. Most of the ones you buy are not going to be that. The one I'm going to teach you, no, we're not dealing with that. So area is a constant. So just pull it out. Now you need to remember the magnetic field of a solenoid. This is an equation we haven't used too much, but I did teach it to you, and it is one you need to know. It's on the formula sheet. The magnetic field for a solenoid. Again, just to show you all, there is 3 magnetic field equations I've taught you all. One is for a straight wire, one is for an arc of wire, and this last one here, that's the one for a solenoid. Mu naught, capital N, I over L. So mu naught, so we're going to do D, we're still taking the quote-unquote derivative here, of mu naught N, I over L, and we're taking that with respect to I. This is a very easy derivative.
Is that A?
Area. A is area. I pulled it out because it's a constant.
Oh, but it's not next one.
No, it just goes in the front. It is a constant. But as the current changes, the field will change. Yes, that is a great point. The magnetic field in the solenoid is constant, assuming a constant current. But if the current changes, then the field will change. Yes. All right. Very easy derivative. Mu naught is a constant. N is a constant. L is a constant. In fact, let me just make this even simpler. Just pull those out. Pull out the mu naught. Pull out the N. Pull out the L. Now, I'm not going to use capital L here anymore because I can't use the...
Why did you say n squared?
Hmm?
Did you say n squared?
It can be. I'm just making it, breaking it into as many pieces as possible to make it clear. di over di. What does that equal? 1. Great. There you go. That's the equation for the inductance in a solenoid. The inductance in a solenoid is N squared. In fact, let's just pull the mu naught to the front. Mu naught N squared A over L. That's one way to write the inductance. There's another way. N equals capital N over L. Now, I used the lowercase l. I told you it was kind of unfortunate that capital L is used here. Lowercase l is the length of my solenoid. Capital L is the inductance of the solenoid. It's very easy to mix those up.
What's the difference between big and little one?
Yes, big N is how many loops. Little n is how many loops per meter. Kind of like a density of the loops. How tight packed are those loops? And so you can use this to rewrite the equation another way. So if we remember that N equals capital N over L, that means that capital N equals lowercase n times L. And so that means this is mu naught N squared L squared A over L. One of the L's cancels, so you get mu naught N squared LA. These are the exact same equation, just written with lowercase n or capital N. I only give you one of these in the formula sheet, so just remember that you need to know this relation between lowercase n and capital N. What's up? Yeah.
How does the outline that's on the bottom turn to ln squared at L?
So we replace capital N with lowercase n.
Oh.
Yeah, and that's where it came from. So, this is how you determine the inductance of a solenoid. So there's the derivation, it's in writing, boom, there's the equation, and there's both versions. If you have a solenoid, i.e., if you wrap a bunch of wires around a loop, this equation tells you the inductance of it. Specifically, what is inductance? It's going to tell you how strongly it's going to oppose a changing current. The bigger the inductance, the better job it's going to do at opposing a changing current that happens in the circuit. That's the idea here. At the very beginning, it kind of sort of doesn't, no, not really. No, it can never fully stop it. Because if it stopped it, then the rate of flow would be, it just doesn't. Just like that falling bar never fully stops. Yeah, that's a good question. The angle was 0 because it's the angle between the magnetic field and the area vector. So in that picture I drew of this, the magnetic field is to the right, and the area vector is also to the right. So the area vector is like for one of these coils. And the area of the magnetic field is the magnetic field made by that solenoid. The whole idea here, though, just to connect it to last week, is that each of these loops is trying to make a field. Every other loop doesn't want that field, and so it's kind of fighting self-inductance. It's kind of fighting itself. And this is useful. Again, the crazy thing here is this is just a wire spun into a circle. And I'm spending all this time just teaching you about a wire spun into a circle, something an elementary school student can take. It's not a complex device. It's just a wire wound up. But the consequences of this electronically, we had to go through you had to learn a lot of things to understand the consequences of this electrically. And it's very useful. So this is the cool thing with engineering, is that really simple looking devices, you sometimes have to understand a decent amount to understand how they actually work. For example, another device that we're not going to learn in this class, it's called a piezoelectric material. It's a really cool material. Piezoelectric material is really simple functionally. The way they work is when you squish them, they make a voltage. Or when you stretch them, they make a voltage. Why does that matter? The opposite is also true. When you apply a voltage, you can squish the material. When you apply a voltage, you can stretch the material. Why is that useful? You can basically get really precise movements using this. How does it work? Very complicated in terms of it has to do with the structure of the material and a bunch of things like that. But conceptually, it's just, hey, I connect it to a battery and it gets a little bit bigger. Why complicated? All right, so there you go. There's the inductance. What's very, very important here is this does not depend on the current. Nowhere in this equation is an I. I know the lowercase l looks like an I. It is not an I. It is L. It doesn't depend on a solenoid. If you go to a store, you will buy a solenoid, an inductor, and it will have a set inductance. How will that inductance be determined? By how many turns it has, by the area of the solenoid, and by how long the solenoid is. Those three variables. There is one other variable we're not going to get into. If you put an iron core inside of this, it does amplify its ability to oppose current. Just like in a capacitor, when you put a dielectric, it boosted the performance. We're not going to get into that though. For now, we're just going to worry about the geometry, not whether or not you put an iron core in it, though that does help. And yeah, the next slide is just showing you a bunch of pictures of solenoids. So here's what they look like in circuits. This is like functionally what they look like. These guys over here are toroids. A toroid is just a solenoid that got looped back kind of on itself. If you take a slinky and you loop it back on itself, that's what this is. But we effectively treat all of these like solenoids, even though they're not infinitely long solenoids, but it's fun. So a lot of these kind of look like what you'd expect. Something that's kind of fun is your charging pads. Something you might not consider. How does wireless charging work? It's Faraday's law. How does wireless charging work? You have a bunch of loops of wire. I put current through it. I put a changing current. It has to be a changing current. When I make a changing current with time, I make a changing field with time. Inside of your phone that has wireless charging is another loop of wire. It experiences a changing field. It doesn't want a changing field. So it makes a field to counteract that. And that's wireless charging. You've now induced a current in your phone without actually connecting any terminals. So again, another thing that everyone is using nowadays, and 99% of people have no clue how wireless charging works. And they don't need to. But as engineering, that should be something you should look at the world and say, how does this device work? How does this device work? Even things as simple as a coffee maker and things like that. Every single thing that a human has made, a lot of thought went into that device. So engineering, you should think about that. Physicists, you should be curious how the world works. I mean, I say should be. Depends what you're in it for, right? Depends if you actually enjoy it or if you're in it for the money. There is different motivations in life. But if you want to enjoy it, you should be curious. Yeah, and then there's other devices. I have no clue how these ceramic ones work. Honestly, I don't. But hey, look into it. Google it. Have some fun. Be curious. All right. Let's see if this makes sense. Very simple problem, just very simple math. See if you can do it. Use the equation. A solenoid that's 50 centimeters long has 500 turns of wire. These things have lots of wire on them. The more turns, the better. Has a radius of 2 centimeters. What is the self-inductance of the solenoid? You will need a calculator. This is not, you can look at the answers. None of those are nice. And I'll tell you, these clicker questions are kind of the level that inductors are going to show up on the test. They're not going to be complicated questions. They'll be just like the clicker questions. Turns per line. Yes. How tight are those turns? Capital N is how many turns. Lowercase n is the turns per line. Oh, yeah, great question. Do you need to convert the units? Always. Always. Rule of thumb. There is every now and then the case where you don't, but that's only if you have to know your equation well to know whether or not the units cancel. Yes. Yeah, always convert your units. It's a good rule of thumb, unless you really know why not to. I can think of something. There was a joke we did in grad school where like the meter, the meter's arbitrary. Someone just said at some point that the meter was going to be the unit for distance. And then we stuck with it ever since. So we made a joke that, what if I just found a stick outside? You named it after yourself and you made every unit of distance measure based on that stick. It's called one Wesley. Yeah. Yep. And that's kind of like the Weaver, the magnetic field. No, Gaussian Tesla. Yeah. Nowadays, I will say it's very hard to discover things. You have to. What do you mean, name-wise? Oh, there's tons of things. You just got to get really deep into the research too. There's lots of new equations named after people, but you're not going to see them because they're for highly specialized use cases. Oh. All right, I'll give you all some 4 minutes. You got 50 more seconds to kind of set this up, plug in the numbers. Not every equation is the. That one will be on the board. All right, 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, so what are we solving for? L. What's the equation for L? We got a couple of them. We're going to pick the one that's going to make the most sense for us in this problem. We got mu naught capital N squared A over L, lowercase l. And we have mu naught lowercase n squared A times L. We actually have another one, which is the one that we started this PowerPoint slide off with, which is epsilon over di dt. And this is a good exercise in determining what's the right equation. What's the right equation? It's the one that you can actually solve. It's the one that you have enough information for. So in this case, let's look at what we have. We have capital N. We have the length, and we have the radius. So that should immediately probably, we're going to use one of these two. Probably the one with the capital N, because we actually have that information. So we're not going to use that one. It's not a bad equation. We just would be extra work for us. The 500 is how many turns? If it said 500 turns per meter, then it would be lowercase n. Remember that n, lowercase n, is capital N over L. So n is how many turns. Lowercase n is how many turns per meter. Based on the equation there, you can see the units there. So, anywho, now we're going to write this one. We're not going to use this one either because we don't have those things. So it's going to be mu naught times n squared times pi r squared. Every single one of these is a circle because that's the easiest way to build them. Makes everything uniform. And then we're just going to plug in numbers. This is the most boring type of problem, most straightforward one, but should also be one of the easiest ones. I'm going to give myself way more room. But these are the questions. There will be a handful of these questions on the test, just like last time. Can you plug in numbers? 4 pi e to the minus 7 times 500 squared times pi. And I still didn't give myself enough room. This is why I try to avoid problems with numbers in them, because they are just a little tedious. Yeah, I could. I'm going to write it all out to be kind. And 0.02 squared all over 0.5. Now, something I've mentioned a few times, I think. When you all set up an equation like this, do not plug it in pieces in your calculator. Plug this entire thing in your calculator. The more times you interact with your calculator and hit enter, the harder it is to keep track of what you did. But at one time, and I even like say it outside, I say it out loud when I'm doing it. Obviously in the test you can't really do that. 4 pi e to the minus 7 times 500 squared times pi times 0.02 squared divided by 0.05. And when you plug it in your calculator, I can then check that what I typed is what I wrote. It's one step. What I typed should look like this if they look the same, and my answer should be correct. Assuming I did the physics correctly. And we get 0.0078. Something's off here. That's why I put 0.0. Look, I'm in. All right. I was harping on why it's important. I didn't actually check carefully. In my calculator, I typed 0.05 instead of 0.5, so I was off by an order of magnitude. It will happen to you. Now I'm correct. So the answer comes out to this. Yeah. Yeah, it's a good question. Do you need to put the ones in parentheses? I just multiplied all these together. No. So like the 4 pi e minus 7, if you type that as is, it will come out correctly. Yeah, it'll do the math for you. I think most calculators, not all. You need to know your tool. Every calculator is slightly different. All right. This is more the question. I mean, I like both of these questions, but I like this one more because it's quicker. What happens to the inductance if I double the number of turns, double the length, double the radius? You know what? Let's just make this and double the amount of current going through it. And that's purely in variables. Just because I say someone changes doesn't mean it affects something. Yeah, that's something very important. All right, I'll give you all till 2:30, so 40 more seconds. Write the equation. Whatever change happens, multiply that number by that value. Be careful of squares. Whatever happens to something, if it's squared, you better square that. All right, in 5, 4, 3, 2, 1. All right, same thing. We're going to choose the equation now for the sake of time. So we got two different ones. We got the same ones I did last time. Mu naught n squared times a over L. We have mu naught little n squared times a times L. Which one are we going to use? The ones that it references. It does not reference the turns per length. It references the total turns. So yet again, we're going to use the first one. And then we put in the change. This is my original. What's my new one? Mu naught is still mu naught. How does my turns change? I get twice as many. My area. What happens to my radius? That gets doubled. My length. What happens to that? It gets doubled. The current doubled. But just because something changes doesn't mean it changes something else. It says current doubles, but nowhere in this equation is an I. So don't plug on. If it's not in there, it doesn't affect it. That's an important thing to remember, y'all. Again, engineering, physics, computer science. The whole world is changing all the time. When I measure the temperature here, I'm not checking the flight, how much the price of tickets are in China. Why? They're not correlated. The whole world is full of variables. Doesn't mean that just because one thing changes, something else does. How do you know what affects something else? The equation. The equation tells you the relevant quantities. The ones that actually affect it. So, just to write this out, the 2 squared, that's going to be a 4. The 2 squared, that's going to be a 4. Then we're left with everything else. The 2 on the bottom is a 2 on the bottom. So, this is my original. Mu naught n squared times pi r squared over L. That's my original. What's being multiplied by it? 8. 4 times 4 is 16 divided by 2 is 8. Great. I have done this in the past where I've given you a problem where something changes and nothing changes. Write out the equation. You have to actually do it. This is I don't know how common this is, but this feels, I don't know, in my mind, if you apply for an engineering job, this is the kind of question they could potentially ask you. Hey, I have some system. I want to make this thing twice as strong. What material should I choose? What area should I choose? What length should I choose? What yada, yada, yada. Some things won't matter. Some things will. You need to know the relevant equations or concepts to be able to determine that. An equation is just a bunch of concepts strung together. It's a sentence. So, you do need to know some of these things. Depends on your discipline what it is. All right. We're going to quickly derive the energy stored in this inductor. There is energy stored in it. It's stored in the field, just like a capacitor has energy stored in the field, electric field. We're going to use these 2 pieces of information, these are not new, except for this LDIDT. This is like a little trick we're going to do. So, yeah, let's remember power is PIV. P equals IV. If you're like, where did this come from? This doesn't look like something I know. You all hopefully know PIV. P equals IV. V is epsilon, I is I. Great. Then we just substitute. What is epsilon equal to? L didt. That's the definition that I gave you at the beginning of this PowerPoint. Yeah, I got rid of the negative because, again, we don't bother with it. All right. Power. And look, it's over there. This is the definition of energy. Integrate your power with respect to time. What is power? It's the rate of energy used per second converted. This is a definition. This is not a new thing. This is like a physics 1 thing. This is how much energy per second. If I multiply it by seconds, I get energy. So this power equals the derivative of energy with respect to time. So rearranging. All right. This is a very quick derivation. Take what's on the left, put it what's in the right. So we get the energy equals the integral from 0 to t of L di dt times I times dt. We're yet again going to do something that seems a little silly, but in physics, we are cool with it. dt's cancel. Why? Because we just treat them like variables, and that's fine. All right, this is such an easy integral. Now, okay, here's the weird part. We're going to change our bounds of our integral. Let's call it like I max. Previously, we were integrating with respect to time. Through the magic of physics wonkiness, we're integrating now with respect to I. What's the integral of I? I squared over 2. So the energy in the inductor is going to be L times I squared over 2, evaluated from 0 to whatever the max current, or whatever the current is. Let's just call it I naught. It was lost in translation. There it is again. All right, so just to write this out. Yay, there's the energy stored in an inductor. That's the one-line derivation. It gets 2 lines if we use the original stuff. There it is a little prettier. 1/2 Li squared. Yeah, they're the same thing. These 2 slides are the same thing. One's just written out.
Wait, I have a question.
I should have a nicer slide on this one.
Why did you write down P equals I? Is it just like conceptually?
That's an equation that we know. So we can use it.
Do you use that?
Yep. I used it to derive this. I used P equals IV, then I changed the V, quote unquote. I'm just reminding you that these 2 are the same thing. Epsilon I, V times I, same thing.
Oh, right.
All right, great. We're nearing the end, y'all. This is the energy stored in an inductor, 1/2 Li squared. Why? Because we derived it. All right, how can I store 4 times as much energy in an inductor? So just using that equation, if I want to store 4 times the energy, what do? Which of these will accomplish my goals? If I use 4 times the current, will that accomplish my goals? If I use 4 times the number of loops, will that work? Half the length, double the radius. You're going to have to use 2 equations here. Yeah, you're going to have to use the one I just gave you. And you're also going to have to use what is the inductance of a solenoid. That's the one we've been using. There's only one right answer. There's just one right answer. All right, give you all 30 more seconds. All right, in 5, 4, 3, 2, 1. Now to answer this, I'm going to need to write what L is. L is equal to mu naught N squared times L A over L. Why? Because we've been using it this entire time. We already derived that. So that's 1/2 times mu naught times N squared times A over L times I squared. All right, if I use 4 times the current, that 4 is going to get squared. That's going to end up with 16 times the energy. Bad. If I use 4 times the number of loops, that's going to get 4 squared. That's also 16 times the energy. Bad. 4 squared. Half doesn't matter. See, yeah, just to remind you all, we're comparing it to what was originally there just because there's the half's there at the beginning and the half's there at the end. Yep, we only care about what changed. The half was always there. So because a few people might have this question. Let me do this one real quick. Here is the original. I'll do it for one of these just to prove this. So that's the original. Yeah. This is the energy. Capital U. All right, the new energy, this is specifically for this one, would be 1/2 times mu naught times n squared times A over L times 4 times 4I squared. So what does this turn into? This is something I do want to point out, so I'm actually glad it was mentioned. 4 squared is 16. Do not combine that with the 1/2. It's very tempting to do that. Do not do that. You're going to see why in a second. So it's 16 times 1/2 mu naught times n squared times A over L times I squared. Why do you not combine it? This entire term, including the 1/2, is the original. If you get rid of the 1/2, you cannot call it the original. So this is an important thing to note. Do not just combine all the numbers together. If there's already a 1/2 there, leave it. All right, half the length, that's going to double it. Bad. Double the radius. Radius is squared. Pi r squared, that's going to do it for us. This is a good exercise to go through, and you can go through each of these and prove why it's 16, 16, 4. If you're not sure, practice each of these situations.
The way I was thinking of it was like, if you want to multiply by the 1/2, the outside coefficient have to be 2. So that when you double the radius and you combine it with the 1/2, you still get 2 on the outside.
I think that's another way of doing it. Yeah, that's fine.
It's just that don't combine the 1/2.
I recommend not combining the 1/2 is the better way of doing it. It's a bit more clear. All right, one last thing I need to teach you is how these behaves in circuits. I'm only going to teach you conceptually how. I will show you the equation for it. We're not going to derive it. But you do need to understand conceptually how these behave in circuits. So in the following circuits, I have a resistor, I have an inductor, and I have a couple switches. When will the inductor resist the current the most? When will it oppose the current the most? And my hint to you all is the thing that we learned at the beginning of class. The first definition I taught you. This voltage, remember that negative sign. Why is it negative? That's the voltage that's going to make the inductor is going to make to oppose. So my question to you is, when is this maximum? Because when this is maximum is when the inductor opposes it the most. There is only one answer. Is it immediately after switch 1? A long time after switch 1. Immediately after switch 2. A long time after switch 2. These are the last few questions we're going to work on, is basically how these behave in circuits. Bunch of quicker questions. Give you a minute and a half on this. This is very important to understand. This is a very important question. All right, 20 more seconds. There's no math here. No math you're doing. You're not multiplying, dividing, adding, subtracting. You're looking at an equation. You're trying to understand what it represents in words. All right. 5, 4, 3, 2, 1. All right. When nothing is closed, nothing is happening. There is no current that's flowing because there's nothing driving the current. If I close switch 2, nothing's going to happen. Absolutely nothing's going to happen when I close switch 2, because the only reason current flows is when there's a high voltage and a low voltage. When switch 2 is closed, it's just a high voltage everywhere. Nothing happens. When switch 1 is closed, something will happen. I currently have no current. When I close it, all of a sudden, I'm going to want a lot of current. This circuit is going to want to pump all that current through it the second that closes. Just like when I flip a light switch, the light immediately turns on. That is when the rate of change of current is the largest, right when I close it. When the rate of change is the largest, so this is di dt equals max. So that is my answer. Now, this will not keep being the case. Eventually, the current will start to increase. And it will not increase forever and ever and ever and ever. At some point, we're going to reach a steady state of current. If we didn't reach a steady state, that would mean that the current would be growing forever. And that's nonsense. So at some point, this di dt becomes 0. When di dt is 0, then my epsilon is 0. It's no longer opposing this. So inductors oppose the current at the very beginning. And then as time goes on, they stop caring. This is the exact opposite of capacitors. Capacitors didn't care in the beginning, and they care after a long time.
And just quick refresher, the little at an epsilon, the smaller tech mark is the negative, right?
Yes, yes. Yep. Negative terminal, positive terminal. Doesn't change anything here. All right. So this is the graph of this. You don't need to know these equations. There's no equations here. So this is just a summary of what I just said. The largest change is when the switch first gets closed. As time goes on, eventually we reach some steady state. And you can see the graph of this. My slope of it turns to 0. When my slope is 0, my value of epsilon is 0 because it's based on the slope. So, all right, there's the equations. You don't need to bother with them. I just want to make sure, this is just to see if you remember from test 1. When does a capacitor oppose the current the most? We're not going to test, this is not going to show up on test 2, but it could show up on the final. I'm just making a comparison between inductors and capacitors. Similar circuit, but now it's a capacitor. When does a capacitor oppose it the most? Is it a long time after switch A is closed, short time, immediately after switch B, long time? Switch B is, so basically, this is switch B closed. This is switch A closed. Yeah, it's depending on where it swings to. If y'all remember, are you in the lab? Are you in the PhD labs? Yeah. Do you remember the RC circuit lab? You all measured there was a resistance capacity, you measured the voltage over time. You could do the exact same experiment on the graph. In that experiment, you measured across the capacitor. If you replaced with the inductor, you would do a different graph, but similar experiment. All right, 10 seconds. All right, in 5, 4, 3, 2, 1. All right. Again, this is a rehash. This is a great question that I can put on the test. So remember, y'all, C equals Q over V. So when does a capacitor oppose this the most? When it has the most charge. When does it have the most charge? When after it's been charging for a long time. They're opposites. That's the key here. That was the takeaway I wanted you to get. An inductor helps oppose the beginning. A capacitor opposes the end. That was the final kind of takeaway. If we did AC circuits, we'd use that, but alas. All right, y'all. Good luck studying. Reviews there. Practice. You know, all that stuff. Don't forget the quiz.
Okay, so the test is going to be on week